I don't know what time is it on. I think 2 or 3 in the afternoon. Is it at 3? Okay. Hi, how are you? We were talking last time about fuzzy logic. And let's kind of review where we are and where we're at and where we're going. With fuzzy logic, we found out it's the theory of partial membership in different sets. And that we don't have a Boolean sense of being in the set or the out of the set, but we actually are more interested in the degree of membership within the set. It is not probability, but a fuzzy membership usually covers all possibilities. Remember that membership function for tall men? It covered men that were 900 feet tall, right? That membership function just kept going. In other words, it covered that possibility even though it was not probable. Hence the idea of probability versus possibility. Zeta originally proposed for the union operation, the maximum, for the intersection operation, a minimum, for a complement, a 1 minus, and we found out the genius of what he did, because what he did was came up with the logic operations that matched all of the boundary conditions except for the law of contradiction, the law of excluded middle. Fuzzy theorists have said that if you make your complement, union, and intersection obey the law of contradiction, obey the law of excluded middle, that something else is going to be violated, one of these other conditions. So it was kind of nice in that sense. Yet despite that, there are other techniques and other methods for performing intersections and unions. And we discussed those last time, and I think the last thing we ended up was with the fuzzy union, the concept of the Jaeger class. This was the Zeta union, and then the Jaeger class, which was something which was not idempotent. Again, if you deviate from Zeta's original one, you deviate from this idea of obeying all of the boundary condition problems. We said that the Jaeger class last time was equal to the minimum of 1 and a to the w plus b to the w raised to the 1 over w, where w took on any value between 0 and infinity. And in fact, what we said was this satisfies all of the axioms except it was not idempotent. Remember what idempotent means? That the union of A with itself should be equal to A. Now, is this such that the union is equal to that? Well, it's equal to the minimum of 2A to the W to the 1 over W. Is that right? If we perform a union of A with itself, we get this result, which is equal to 2 to the 1 over W times A, which is not idempotent, because if it was idempotent, we would like it to be equal to A, wouldn't we? And certainly it isn't. Okay. It's 2 to the 1 over W times A. We also ended up last time by showing that U for W is equal to infinity of A and B was equal to the Zeta union, which was the max of A and B. Right? Is that okay? Okay. You're not laughing at this, are you? Okay, good. What?
Why don't you have a minimum of 1 and 2 in the second one?
Oh, where did this come from?
Yeah, it should have one comma.
It should have what?
1 comma.
Oh, the 1 comma, yeah. Sorry. Yeah. Okay, thank you. Yeah, thank you. That wasn't what was funny, was it? Oh, okay. That doesn't... If it is, I want to talk to you about your sense of humor. Okay, that was, now there's another interesting case, and that is U for W is equal to 1 of A and B. By the way, I always do this, and now's a good point. I make my A's differently, and I've given up a long time ago trying to be consistent. So both of those are exactly equal to the same thing, and I will interchange them without any warning and without noting it. And I see that I've done it here. See the A's all of a sudden, boom, turn to the other A's. So I do both the typewriter A's and the script A's. Okay. W is equal to 1. This is the minimum of 1 and A plus B. Now, this is interesting because this means that we can perform a union in some instances simply by adding the membership functions for A and B. And then if it exceeds 1, we clamp it to 1, we threshold it to 1. We've got to make sure that the membership doesn't exceed 1. Well, this is a type of inferencing called sum product inferencing. Sum product, let's call it logic, if you will. Sum product logic is where the union operation is actually performed by an A plus B, by addition, and the actual intersection operation, as we'll see, is done by a multiplication. And the reason this is very nice is because we have a lot of processors that do this very, very quickly, right? Do additions and multiplies, and we have a lot of software that does that. So sum product inferencing and sum product logic is logic which is used quite a bit. So a special case of the Jaeger union for W is equal to 1 is the sum part of the sum product logic, where the summation is used to perform a union operation. So the Jaeger complement is kind of nice and relatively general, since it includes both the Zeta and the sum product inferencing. Let's look at general fuzzy intersections. General fuzzy intersections. We have, just like in the union case, we have different axioms which we have to obey in order to perform an intersection. We would like it, first of all, to meet the boundary conditions. That is, if we take this fuzzy intersection and we look at it at 0 and 0, we hope to get out a logic 0. And if we look at it at 1 and 1, we hope to get out a 1. So these are the boundary conditions where the fuzzy intersection operation at these points meets the Boolean intersection operation. We hope that it is commutative in the sense that the intersection of A and B is the same as the intersection of B and A. And we'd like it to be monotonic. That is, if we have two statements which are connected by an and the truth of one of the statements goes up, the truth of the compound composite statement should stay the same or go up. So that's what we mean by monotonicity, right? If you have a statement where you have one term and another term, each one of those terms corresponding to a component of that statement, then each component has a truth and the entire statement has a truth. Monotonicity says that if the truth of one of the statements increases, then the truth of the entire statement probably increases, or at least it stays the same. It doesn't go down. So that's what we mean by monotonicity. And the way we write this analytically is that if A is less than alpha and B is less than alpha, then I of AB is less than I of alpha beta. So in other words, alpha and beta have a greater truth than A and B, so therefore the intersection of A and B must have less truth, if you will, or have less of a membership than the intersection of alpha and beta. So this is the monotonicity requirement, and it follows very heuristically from our concept of memberships of the composite terms. We also hope that it's associative. If we perform an intersection of three events, A, B, and C, then it should not matter the order that it's presented. It should be exactly the same. Then we have some supplementary conditions which we'd like to have. One is that I is continuous, and the other one that it is idempotent, in the sense the intersection of A and A is equal to A. So these are the different axioms that we require it to follow, and then it'd be nice if we could have these properties true, I being continuous. There are examples of the Zeta intersection, I of AB is equal to the minimum of AB. By the way, is that a continuous function? Is the minimum of A and B a continuous function? That was one of the properties we'd like. We didn't require it, but is it a minimum function? Is it a continuous function? Anybody hazard a guess?
No.
Huh?
No.
No. Anybody else want to hazard another guess? Yes.
I think it is.
You think it is?
Not the derivative.
Anybody? Huh?
The derivative wouldn't be, but it would be. I would say.
Oh, it's a continuous function without a derivative?
The derivative would not be continuous, but the function would be.
The derivative would not be continuous. I see what you're saying. Okay. But it does have a derivative. Any other? Okay. Well, let's take a look at it. What did we say? The intersection of A and B is equal to, okay, here's A and here's B, and we're just interested in this intersection line along the interval from 0 to 1. Well, clearly we're going to have a line here where A is equal to B, and something special has to happen along that line. If A is equal to the maximum, what did we say minimum, the minimum of A and B, then what is it equal to on this side? I think that B is the minimum over here, isn't it? So over here it's B. So everything here is B. So we actually have a buildup, kind of a ramp going up, with B going from 0.1, 0.2, 0.3. So there's kind of a ramp going up here, because it's equal to B there. Similar fashion over here with B, looks like B1, a vitamin B. In a similar fashion, we have it's equal to A over here. So it's equal to A over here, so we also have a ramp building up here. So we do have a ramp, and the neat thing is that this ramp going up here, this is 0.1, 0.2, 0.3, etc. So it ramps on up to 1. And this ramp meets very nicely on the diagonal here. Now on the diagonal is kind of a cusp in a way, right? Because it's a discontinuity here. But the overall function itself is nice and clean and continuous. And in fact, if we took the derivative of this is kind of interesting. Say take the derivative of the maximum of A and B with respect to A. What's it equal to? It's also differentiable. Oh, I'm sorry, the minimum, yeah. Okay, the minimum. Well, the partial of the minimum with respect to A when it's B is equal to what? Come on. What's the partial of B with respect to A? Doesn't change with respect to A. It's 0. Partial over here is the partial of B with respect to A. B does not change with A. B changes with B, but if you give me a specific value of A, the value of B doesn't change there, does it? So the partial is actually 0, and the partial here, up here, is equal to 1. So we're actually left with a plateau, and up here this plateau at least is equal to 1 here, and it's equal to 0 on the bottom. Okay? So we have a situation where, as was mentioned, that indeed we have a continuous function here, but the first derivative does exist, but the first derivative is not continuous because here we have a shelf that we fall off of, right, along this line. So yeah, indeed, the minimum operation is a continuous operation, as you might think the maximum operation is also. Let's take a look at the intersection. We have the Zeta intersection. Let's look at the Jaeger intersection. You look at this and you go, whoa, is that weird? Nah, but it works. It's kind of neat. Can anybody see how the Jaeger intersection was motivated by the Jaeger union? He kind of used a De Morgan's law. He kind of used the De Morgan's law in that the intersection of two variables is equal to the complement of the complements of the union, right? So in essence, it was motivated by a De Morgan's law. In other words, it was motivated by this, A intersect B is equal to A bar or B bar complement. That's De Morgan's law, right? And this is exactly what he did. Here's A bar, here's B bar. This is the union of A bar and B bar by our previous definition. And then we do this big complement, which is the 1 minus. So it's kind of it's motivated by De Morgan's law, although it isn't an actual direct application. Yeah.
Isn't the Jaeger complement different than that complement there?
Ah, good point. Yeah, we're assuming here that we're not using the Jaeger complement, that we're using the conventional 1 minus complement. Yeah, that's a good point. For which one? Which homework assignment? De Morgan's law for this, to see if De Morgan's law is applicable to this. This we will talk about as the Jaeger. Oh, I see. In the De Morgan's law, you need the complement. Use the 1 minus complement. Make it easier. Okay. Thank you. Now, just like before, we can show that I sub infinity is equal to the minimum of A and B. Which is very interesting. The question is, do you think that the Jaeger intersection is associative? If it is, it's not apparent, is it? Why don't you take a look at that? See if you agree that it's, see whether you think it's associative. Is that one of the homework problems? Okay. That's what I thought. It's interesting, though. It really is interesting. Is it associative? So that's the Jaeger. And then for some product inferencing, the product part is not a special part of the Jaeger intersection. For some product inferencing, the intersection of A and B, let's call it some product, is equal to A times B. Just a simple multiplication. Let's check this off as far as the axioms are concerned. Does it obey the boundary conditions? We actually went over this a couple lectures ago. Does it obey the boundary conditions? When A and B are both equal to 0 and 1, does multiplication give you the traditional table of the logic AND? Yeah, it does. Is it commutative? Yeah. Is it monotonic? You increase one of them, the whole thing increases. Yeah. Is it associative? Sure, because multiplication is associative. Is it continuous? Yeah, it is continuous. Is it idempotent? No. No, because the intersection some product of A with itself is equal to A squared, which is not equal to A, which is the requirer of idempotence. But it does, the sum product inference does meet all of the requirements of the boundary conditions of the fuzzy AND. And again, just to show you the union for the sum product is equal to, we had it over here, the minimum of 1 and A plus B. And the complement is just the 1 minus for the sum product inferencing. Now here's something which is very interesting. We're going to actually revert back to the union, but it's also true for the intersection. But no matter what union you use that obeys all of these axioms, it is going to always exceed the maximum. In other words, there's a theorem that says that the union of A and B is always going to be greater than or equal to the maximum of A and B. And what do we mean by the union of A and B? Any union which defines the axioms which we stated. Any union that defines that follows the axioms that we stated obeys this. It always is in excess of the maximum of A and B. Now I can prove this, or I can just put it in the notes. I think I'll just put it in the notes. Okay. Unless you want to see a proof. It's one of those proof by contradiction. I think I'll just go ahead and put it in the notes, and you can take a look at it. But in a similar fashion, what do you think about the intersection? The intersection of A and B is less than or equal to the minimum of A and B. I'm sorry, greater than? I'm going to put a question mark there. And I think you'll probably see this in your next homework, because I'll give you this one in the notes and then just ask you to look at this one. It's usually a dual sort of proof. Everything that we've looked at thus far, the intersections, the unions, all of the combinations. By the way, before we go on, what do you think would be a good fuzzy XOR? That's an interesting one, right? Not an OR, but an XOR. What would some of the properties of an XOR be? If you had one fuzzy set with a membership which looked like this, and you had another fuzzy membership which looked, I don't know, something like this, what would you expect the XOR to look like in such a case? Well, where it was 1 and 1, you would hope it would be what? It'd be 0. Here's 1 and 0. You kind of hope it to be 1. 1 and kind of a half, I don't know, somewhere between a half. 0 and 0 should be 0. Right? So do you have something that looks good? Something which kind of goes like this. Let's see, 0 and 0, 1 and 1. So anyway, the point is where they're both 1, it should be 0. Where they're both 0, it should be 0. Where they differ, and one is 1 and the other one is 0, let's make this come down a little bit faster so that this is 1 and that's 0, it should be equal to 1. So we have those points. So we need something in terms of the operation that kind of fills in these points in a way. Does that make sense? And it should be such that it matches some sort of boundary conditions corresponding to the crisp XOR. Okay? Should be continuous in some sense. And it should obey all of the axioms which go with the XOR and the union. I will ask you next time to think about what you think might be a good candidate for an XOR. As we have seen, there are really no correct answers, because we've seen that there's a number of them that actually go along and satisfy the axioms. So this isn't one with a correct answer, and you won't find it on the web either, I think, in any textbook. It's an interesting problem. Now, all of these that we have looked at thus far are referred to as aggregations. All of these, what do I mean by all of these? The unions and the intersections and the Jaeger intersections and all of these other things. Aggregation means the following. You have a number of items and you try to concatenate them into a single number. You don't want to look at everything. Rather, you want to look at a representation of everything. Many times we use aggregations such as the mean. Okay? There's other ones. Sometimes we use a geometric mean. Multiply n numbers together and take the nth root of it. That would be another aggregation. We could take the minimum of all the big list of things. We could take the maximum of the list of things, each one of them in a sense giving a representation for the list of numbers. A single number representing a bunch of numbers. That is the concept of aggregation. Not aggravation, it's more like the word combination. By the way, I think before I get into aggregation, we mentioned these. I gave you the answer. Okay. Sorry, I gave you the answer. I of AB is less than or equal to the minimum. We mentioned again the genius of Zeta originally, that the maximum is the only union operation satisfying all four axioms and two supplementary properties, including idempotence and continuity. The minimum is the only intersection operation satisfying all four axioms and two supplementary properties. Now, in these properties, not included is the law of excluded middle and the law of contradiction, because the min and the max don't do this. But we do, however, well, this is what it says here. Recall that the minimum violates the law of excluded middle and the max violates the law of contradiction. And then we have the Whack-A-Mole principle, which is the fuzzy set operations of union, intersection, and continuous complement that satisfy the law of excluded middle. You can manipulate, you can find other intersections and unions to satisfy the laws of excluded middle and law of contradictions, and you can make them do that, but they will not be idempotent if you do it. So in other words, if you try to push down the law of contradiction, satisfy the law of contradiction, you try to satisfy the law of excluded middle, you're going to violate something else, which in this case is idempotence. So as one thing gets satisfied, another one pops up. So it's just one of those cases where you cannot satisfy everything that you would like to satisfy in terms of your definitions. Some talk about this as being a weakness of fuzzy logic. You can decide for yourself. I personally think that in terms of excluded middle and law of contradiction, that actually kind of makes sense in a linguistic formulation. So it doesn't bother me that much. Okay, aggregation. Here's aggregation. We're going to take a bunch of numbers, and H is going to be a mapping of numbers between 0 and 1 to the n numbers into a single number between 0 and 1. And that's what we've been doing. When we take the maximum of n numbers, we are taking a bunch of n numbers and we're doing a mapping, and the mapping in that case is the maximum to another number between 0 and 1. In the similar case, we do this with the minimum. We also do it with the average. If we add them up and divide it by the total numbers, that's the mapping of a bunch of numbers between 0 and 1 to a number between 0 and 1. And what we would like to do is to have this aggregated single number be in some way representative of the entire string of numbers. There isn't a unique way of doing this, but there are some boundary conditions that we would like to have. One is the boundary condition if we aggregate a bunch of zeros. Everything on our list is zeros. And we aggregate all those zeros to be represented by a single number. What should that single number be? Should be 0, shouldn't it? Right? Similarly, if we aggregate a whole big list of ones, it's got to be a 1. Come on. Monotonicity. If we take the string of numbers and we aggregate one string of numbers, and then we substitute one of the numbers with a smaller number, this new aggregation should be smaller, or at least the same as the original one, right? If you take that big list of numbers and you get an aggregation, let me do the converse of it. You take a big list of numbers and you get an aggregation at the bottom. You take that same list of numbers, except you take one number out and put a bigger number in, then your aggregation should be bigger than the first one, because you made one of the numbers in the list bigger, right? Or at least it should be the same. It can't get smaller. So this is what this monotonicity argument is saying in terms of monotonicity. Now, this is something that we saw both with the minimum and the maximum, was this idea of monotonicity. It doesn't matter whether your statements in fuzzy logic are coupled with an and or an or. If the truth of one of the portions of the sentence increases, then the truth of the entire sentence increases, or it stays the same. So we'd like to have it monotonic. We'd like to have it continuous. It doesn't make sense for it to be non-continuous. And we would like to have be symmetric under permutations. This is a type of commutivity in the sense that we would like the aggregation of 1, 3, and 6 to be the same as the aggregation of 3, 6, and 1, or any combination of the numbers. Combination should not matter. This is, again, a type of combined associativity and commutativity sort of property. Now, there's a very nice general aggregation called the generalized mean, and which we will talk about. This is an aggregation operator parameterized by a parameter alpha of a1 through a sub n, where a1 through a sub n all lie in the interval of 0 to 1. So you can think of them as fuzzy membership functions. And the generalized aggregation is this. This can be shown to satisfy all of the axioms that we talked about, in the sense that if all of the a's are 1, let's just go through them really quickly because it's kind of evident. If all of the a's are 1, what will the aggregation be? 1. Right? If all of the a's are 0, what will the aggregation be? 0. So it does indeed meet the boundary conditions. Remembering that each of the a's lies between 0 to 1, let's check the monotonically increasing. If we have an aggregation and we increase a1, will we increase the aggregation, keeping everything else the same? Yeah, we will. Right? So that makes sense. Is it a continuous function? Yes, it is. Is it symmetric under permutations in the sense that if we shuffle these a sub n's, do we get the same result? Yes, it obviously is. So it satisfies all the axioms. The nice thing about the generalized mean is that we have a lot of interesting special cases. H minus infinity, alpha can go between minus infinity and infinity, but H sub minus infinity is actual equal to the minimum of all of the operations. And I had this as a homework assignment, but I did not put the alpha is equal to minus infinity. I put the alpha is equal to infinity. So it should be a minus infinity here in the homework statement. H infinity, on the other end, is equal to the maximum. We kind of showed this before with L'Hopital's rule. H1 is also interesting. H sub 1 is nothing more than the arithmetic mean. Or the average. One that is very interesting is H sub minus 1. I'll put it down. You can tell me what it means, where you've seen it before. Have you seen this before? It's resistors in parallel. right, is the way double E's look at it. And it's a type of aggregation referred to as a harmonic mean. And then one which is really interesting is H sub 0, which is something that you would not expect. It is equal to the product of all of the terms raised to the 1 over nth power, which is the geometric mean. So the generalized mean, this isn't obvious, is it? It's not obvious to me that this follows from that, right? How does this addition become multiplication? Weird. But the interesting thing is that you can think of having yourself an aggregator with a little switch alpha that goes between minus infinity to infinity, where you're aggregating and you're putting together all of these numbers. Well, you turn this switch all the way to minus infinity, you get the minimum, you start pumping it up a little bit, you get to minus 1, you get the harmonic mean, you get to 0, you get the geometric mean, you turn it over to 1, you get the arithmetic mean, and you crank it all the way up to infinity and you get the maximum. And all of these are special cases of this generalized mean for different values of alpha. Very interesting property. And there is a monotonicity that's associated with it, in that this H sub alpha always lies between a minimum and a maximum. This H sub alpha always lies between the minimum, which is the minus infinity, and the maximum, which is the plus infinity. How would you prove this? H sub 0. Let's just outline it for a second. I might give it to you for homework. It's a L'Hopital problem, as you might expect. If we want H sub 0, we would have the summation of n of something to the alpha. Well, it'll be something to the 0th power. So this would be n times 1 over n. So the thing in brackets would be what? 1. Right? The thing in brackets would be 1. 1 to the infinite power. What's 1 to the infinite power? It can be anything, right? And it's a candidate for L'Hopital. You take the logarithm. Do you remember this from calculus? You take the logarithm, apply L'Hopital's rule, and if you turn the crank correctly, this will pop out. Is that evident? How many would like me to do it? I'll do it if 5 people want me to do it. No one! Okay, we'll move on. I'll give it to you for homework then. Okay, I want to return to fuzzy sets. I was unable to download my slides because I goofed up in having access to them here today. So I don't have the overhead slides, but I do have the notes that are associated with them, and I'll walk you through them as best we can. We're returning to fuzzy sets, and we're going to be talking about different operations on fuzzy sets. By the way, we are building up tools to where we will be able to look at the basic fuzzy inference engine, which lies at the bottom, or is at the foundation of the control software that's used to drive everything from bullet trains to electric rice cookers to, gosh, what are some of the other products? Fuzzy washing machines, fuzzy carpet heaters, so you can walk around in your bare feet and keep your feet warm. They like that in Japan, I guess, right? Because you're supposed to take your shoes off a lot. So we're building up to that, and we're building up to this fuzzy inference engine, which takes linguistics of an expert and actually makes it into a very nice algorithm using fuzzy logic that you can apply. And it's really interesting because it's good solid control theory, but it doesn't have any Laplace transforms. There's no poles or zeros. You don't have to know calculus. It's kind of control theory for dummies in a way, and it works really well. So that's okay. Okay, let's talk a little bit more about fuzzy sets. We have talked about the fact that fuzzy sets are a generalization of crisp sets. In fact, if you look at all fuzzy sets, we can kind of see the crisp sets are a special case. Crisp sets are a special case because crisp sets correspond to all fuzzy sets where the membership functions are binary. They're either 0 or 1. We can obtain crisp sets through fuzzy sets. In fact, this is a way much of our Western law is made. And we do this with a process we call alpha cuts. We might, for example, have a, let's see. Okay, here's the membership of being drunk as a function of blood alcohol. Okay? Function of being drunk, membership of being drunk is a function of blood alcohol. Blood alcohol is not the perfect way to determine you're being drunk, because if you drink a lot, it doesn't matter as much. Some people tell me, I don't know. But anyway, we have something which goes like this. And if you have, would we all agree if you have 10% blood alcohol, you're drunk? You're probably dead, right? Okay, 10%. And I think, what is it in the state of Washington? 0.08. Spoken by a man who knows. Huh? Okay, 0.08. Okay, so this is kind of drunk, and I don't know where you might put this on your relative drunkenness schedule, but this might be a 0.9. And we get a little drunker, and we're up here, and we're 0.95. 0.7 might be a 0.6. I don't know, something like that. We all agree that it's monotonic. The more blood alcohol you have, the more you're drunk. Now, what happens is that there isn't a law which says that gives you gradual fines. The drunker you are, the more in trouble you get. No. What they do is they take a crisp alpha cut of this, and they say, I'm going to do the following. I'm going to choose a value of alpha is equal to 0.9, and I am going to take this alpha value, I'm going to extend it across here. Any place that exceeds the threshold, I'm going to put in the set. Everything which is below the threshold is out of the set. So I'm going to threshold this operation and come up with a very nice binary crisp membership function, which in the state of Washington looks like this. So you can see this is referred to as an alpha cut. It takes a fuzzy set and it makes, by performing a threshold operation to the fuzzy set, we actually generate a crisp set, an underlying crisp set that we can talk about. We might also talk about, since we're doing driving, the membership of safe driving speeds as a function of your velocity. Suppose you're on the interstate and you have something like this. You might say that, I don't know, what's the safest driving speed? Flow of traffic. But we don't know the flow of traffic. What would you say if you said it now? 60? In Seattle, 55, okay? 55 is optimally safe. Now it goes down, and I think we can all agree that if you're on Interstate 5, you're going 15 miles an hour, that's not very safe, right? Right? And it's about not as safe as going 100 miles an hour. Okay? So this would be, for example, a set of, and probably this 55 doesn't even reach a value of 1. It might be a little bit below 1 since it isn't 100% safe. We don't have 100% safe. But again, what does the law do? The law does an alpha cut. And the law says, at least through this interpretation, this is not what the law does. There's not lawyers doing alpha cuts. This is just our explanation of the concept of an alpha cut. It sets a value of alpha, and it says, okay, you can't go more than 70 miles per hour, and you can't go less than, say, 45 miles per hour. because what it has done is it has performed a threshold at this value of alpha, and has taken this fuzzy set and it has made a crisp set out of it to make it into a Boolean function. And this is just the way that our justice system works. At a trial, what? You're guilty or not guilty, a 1 or a 0. There's no in between. You can also use cuts to make 3-value logic, Lukasevich value. There's really nothing to say that we have to only do 2 cuts. We can do 3 cuts. We'll call this alpha beta cuts. And let's use the safe driving again. We can actually use one alpha cut, say at 0.9, and another alpha cut at 0.5, and actually generate a 3-layered logic. The 3-layered logic would be something like this. Right? Wherein this would be, I guess I should go actually up to 1. Wherein we would say in this region you are the most safe, and in these regions of velocity you're pretty safe. Okay? So we have again the classic Lukasevich logic, wherein we have 3 levels. We have totally in the set, totally out of the set, and kind of halfway in and halfway out. So you can make 3-level logic. You can see you can make 4-level logic, 5-level logic, etc., which really exposes the fuzzy membership function as being a membership function which is of an infinite valued logic, because it takes on all of the possible values between 1 and 0. So this is the concept of an alpha cut. These are sometimes referred to as alpha and beta cuts. Since one is an alpha cut, the other one's beta cut. I guess if you do 3 cuts, you get alpha, beta, gamma cuts. I don't know what happens when you run out of alphabet, which I guess you can do. Anytime we talk about sets, we typically talk about the concepts of convexity and the convexity of the sets. Fuzzy sets are no exception. Let me review what we mean by a convex set in the crisp sense. Then we'll extend this concept to fuzzy set combinations using or a convex combination of a fuzzy set, wherein the combination is actually fuzzy. And then we'll talk about fuzzy convex sets themselves. Okay, this is for crisp convex sets. For crisp convex sets, let's talk about a set S. If A is in S and B is in S, and we should put a for every, sorry for the mathy stuff, this means for every A in the set and every B in the set, that lambda A plus 1 minus lambda B is in the set for all lambda between 0 and 1, then the set is said to be convex. It's a definition, so it's an if and only if. That's a lot of mathy googly goop. Let me draw you a picture, which is what everybody thinks about when they think about math anyway, is a picture. Once you see the picture, this will become relatively clear. It says the following: suppose, just for illustration purposes, that we look at the S as a set of points within some geometrical figure. So here might be a set of points S, and the set of points corresponds to all of the points inside of this closed oval. It says that if A is an S, okay, here's A and S, and B is an S, then all of these points are within S. Well, this formula here is just a fancy way of writing down if lambda goes between 0 and 1, it's a fancy way of writing down all of the points in the line segment connecting them. That's all it is. In fact, you will notice that this is lambda is equal to 1 down here. If you put lambda is equal to 1, you get A, right? If you put lambda is equal to 1, you get A. If you put lambda is equal to 0, you get B. If you put lambda is equal to half, you get the midpoint. So you can see the dial as you move lambda from 0 to 1, you just move along the point in the path B all the way to A. So that's what the interpretation means. It means that we have a convex set if for every 2 points you choose within that set, you draw a line segment, that line segment is totally subsumed in the set. That's what convexity means. This is a convex set. So no matter where I choose the points, if I draw a line segment, it'll be totally subsumed, totally contained within the set. So this is convex. We have something which looks like this. Well, there are points such as here and here where it's totally in the set. However, it has to be true for all points, and if there's one exception, it's not convex. Clearly, we can choose a point here and a point here, A and B. We can connect these 2 points. A portion of that is outside of the set, so therefore this is not a convex set. Convexity was considered by Zeta in his original 1965 paper, which I plan on scanning and making available on the web for your enjoyment and entertainment. It's really fun reading, especially now after nearly 40 years, 35 years, 37 years of doing stuff. Let's then talk about, we're going to apply the concept of fuzzy sets to convex sets in 2 ways. First of all, we're going to look at 2 fuzzy sets, and we're going to do a fuzzy combination of them. Then after that, we will look at a fuzzy convex set. Both concepts, again, originally introduced by Zeta. A fuzzy convex combination of 2 sets, Zeta used actually F's for his fuzzy set, his fuzzy membership functions. We've been using mu's. Let's use F's here. Then we're going to have a third fuzzy membership set. All of these are fuzzy membership sets, 3 fuzzy membership sets. And we are going to do a fuzzy membership combination. Where the fuzzy membership combination of A and B using the fuzzy metric lambda as a function of x will be equal to f sub lambda of x, f A of x, plus 1 minus f lambda of x times f sub B of x. You'll notice the similarity between this and the definition of convex sets that we had previously, which we said, remember, it was like lambda A plus 1 minus lambda B. We have a similar sort of structure here for this convex combination. Let's explain and see what it means. Let me look at especially the specific case, just for pedagogical reasons, where f lambda is equal to a half. F lambda is equal to a half. By the way, A, B, and lambda can be any fuzzy convex sets. Suppose that we had f sub A look like this, and we had f sub B look like this. So these are 2 fuzzy sets as a function of x. Now, if lambda, if this function was equal to a half, what would the convex combination be? The convex combination would be a new fuzzy set, and this new fuzzy set would be a half of FA plus a half of FB. So in other words, it would just be the average of these two functions, which would look like something which would look like this. You notice where they cross over, what's the average here? It's equal to that. So this is the fuzzy membership of A, B, with the lambdas equal to a half. It is a type of combination of different sets into a set which are representative of both. And in general, you will have convex combinations lying between the maximum. This will always be the case. The fuzzy combinations will always lie between the maximum and the minimum. So indeed, any curve that you can draw between the maximum and the minimum will correspond to a convex combination of the two sets. Let me illustrate that a little more specifically. Here we have A, and here we have B. On the top here, we have the maximum. And on the bottom here, we have the minimum. And any curve that you can draw, any function that you can draw between these two, turns out to be a fuzzy convex combination. So I can take my marker and I can draw any strange looking function here, and that is a fuzzy combination. In fact, I can find a lambda, a fuzzy membership F sub lambda, that will give me this relationship with no problem at all. Okay? So this is the concept of fuzzy convex set combination. And the fuzzy set combination is always lying between the minimum and the maximum. So that's actually something we can prove relatively easily, that the minimum of FA and FB is less than or equal to this combination, is less than or equal to the maximum of FA and FB, which is the Zeta intersection and the Zeta union. So the convex combination is another type, if you will, of aggregation of two or more sets. Now, the fuzzy combination can actually be done for any set of three fuzzy sets. We can also talk about the concept of a fuzzy convex set. Before we get into fuzzy convex sets, you'll notice that all the membership functions that we have drawn so far have been basically one-dimensional. We've done one-dimensional sorts of plots. There's really nothing to say we can't have two-dimensional fuzzy membership functions, such as we did for the outer product Cartesian coordinate, Cartesian expansion. We can look at the set of lakes that are deep and wide. Lakes that are deep and wide. Well, you have two parameters here, deep, which is a fuzzy linguistic variable, and wide, which is a fuzzy linguistic variable. So we can actually think of this as a two-dimensional function, and this two-dimensional function would be a membership function that might reach a threshold of 1 out here. It would be monotonic and kind of go between 1 down to 0 in here, right? It would be kind of a strictly increasing thing. Now, I guess you'd want deep and wide. So you can have a deep lake that is an inch wide. That's not deep and wide, right? That's deep or wide. So you might have 0 along here and 0 along here too. So anyway, the point is that just like in probability density functions, you can generate these fuzzy membership functions in terms of contours. So the contours I drew probably aren't good ones. probably they would be more like this, I guess. Deep and wide. Or those would be 0. Does that make sense? So we have a mountain range here. Now, if we have a mountain range and a two-dimensional fuzzy membership function, what does an alpha cut correspond to? I feel like a rapper there. What does an alpha cut correspond to? It means you take the mountain and you do a slice at a certain elevation. Everything above the elevation goes to a 1. Everything below the elevation goes to a 0. So, for example, if we were to come over here and take an alpha cut of this, say that this was the contour of 0.9, if we were to do a alpha cut of 0.9, we would generate the crisp set, which would look like this. Okay, this would be a certain classification of lakes that were deep and wide. Would be inside here, and it would be 0 on the outside. Is that okay? So this would be an alpha cut. It would make this fuzzy set a crisp set. Now you notice the way I've drawn this alpha cut is a convex set, right? The alpha cut is a convex set. It turns out that you have a fuzzy convex set if all of the alpha cuts are convex sets. So one definition of a fuzzy convex set is that all alpha cuts are crisp convex sets. That's one definition. Makes a lot of sense. If there exists one alpha cut for which the corresponding crisp set is not convex, then you don't have a convex fuzzy set. Now let's extend this to one dimension, because it's not as illustrative in one dimension. In one dimension, a convex set always has to be like this, a crisp convex set. Always has to be this way in one dimension. Because if we choose a point here and we choose a point here, we're saying that all the points between them, here's the point A, here's the point B, all the points between them have to be in the set. So this is a membership function of a convex set. Now it turns out that if we look at the lower point and the upper point, that the upper point can go to infinity, the lower point can go to minus infinity, or both, and it's still a convex set. But all one-dimensional convex sets look like this. If they were bimodal, if you had two bumps, then you could always choose one point in one point in the other, connect the points, and you'd have a point outside the set, wouldn't you? But it's less illustrative, I think, in one dimension to look at the concept of convexity as it is in two dimensions, because you can always draw those line segments that we have in two dimensions. So this is the concept of a fuzzy convex set. I think what we'll do is stop here, and we'll pick up here next time and go forward, and we'll probably actually start into fuzzy inference and finish up the introduction and the fuzzy inference aspect of the course maybe within the next 1 or 2 lectures. Any questions on the homework at all? Homework's to do next time we meet. Okay, thank you for your attention. We'll see you on Thursday.